Hello, this is Roger Cook at Resources for the Future, and this is a little video illustrating an article that is appearing in Climatic Change entitled Probabilistic Reasoning about Measurements of Equilibrium Climate Sensitivity. So this is part of an effort to develop tools to support value of information studies. And this particular video will focus on a number of themes, the first of which is dealing with disparate lines of evidence. Now, disparate lines of evidence frequently arise when we are measuring different proxy variables for the same variable of interest. So in the current case, the variable of interest is equilibrium climate sensitivity. It has a distribution given by this histogram right here. This is the Rowe-Baker distribution as mandated by the U.S. Social Cost of Carbon computing platform. The mean value is 3.29. The standard deviation is 1.24. And equilibrium climate sensitivity is the amount by which the global surface temperature of the Earth will rise as a result of doubling the atmospheric concentration of CO2. These are degrees centigrade, of course. Now, we can't measure this variable directly, but we can measure two other things. First, over here, decadal temperature rise. According to the theoretical models underpinning this whole social cost of carbon memo, there is a theoretical relationship between equilibrium climate sensitivity and decadal temperature rise, and also a theoretical relationship between climate sensitivity and decadal percentage change in CRF. However, these relationships are perturbed by natural variability. So the situation is as follows. Theoretically, temperature at time t is a deterministic function of ECS and T. So if we knew with certainty the value of ECS, we would know with certainty what the global mean temperature would be at any time T. However, if we put thermometers around on the surface of the Earth, those measurements will be perturbed by natural variability in the Earth's climate system. But this variability can be quantified and taken into account as expressed in this term here, sigma nat. And because of that, we can represent the relationship between temperature at time t and ECS as a correlation, which is computed with this simple formula, which I'm not going to explain further here, but just to point out that we can quantify the effect of natural variability and use that to express the strength of the relationship here between climate sensitivity and these proxy variables. So that's something that's good to realize. And the second theme of this little demo is to illustrate the relation between the current and the enhanced measuring systems. We have already systems for measuring decadal temperature rise and decadal change in CRF, and these are indicated here with these pink systems. These are the current systems. And the engineers at NASA have been developing enhanced systems to measure these proxy variables. All of these measurements will be perturbed by measurement error. And this can be things like calibration drift, on orbital decay, and so forth. However, the enhanced systems are designed to be much more accurate. The third theme of this little demo is to illustrate anomalies with discordant measurements and also anomalies with concordant measurements. In both cases, our naive intuitions about how to combine measurements will lead us astray, and it's examples like this that teach us how to think about discordant and concordant measurements to be prepared for apparently surprising and counterintuitive results. Now, the system which forms the basis of all these computations, is called CLARREO Pathfinder, and I'm not going to go into that in any detail, but I hope that if you're interested in this, you can follow the links and the references in the article and learn more about it. The computing platform that is used to illustrate these features is called UniNet, and it has been developed at the Delft University of Technology. So let's get started. Our situation is we're going to launch the satellites in 2020, and we're going to consider observations in the year 2050. Now, in 2050, we've had 30 years of observations. That's a fair amount of time to observe trends. And as a result, the effect of natural variability has been greatly attenuated because natural variability typically has timescales in the order of 10 years. So you see that the correlation between the climate sensitivity and the proxy variable, decadal temperature rise, is 0.96. So this is a fairly strong correlation. Over here, it's 0.94. So that means after 30 years, these proxies are pretty good in terms of measuring climate sensitivity, even taking account of the natural variability. So if we could observe these proxy variables without instrument error, we would be in pretty good shape, at least as regards climate sensitivity. However, down here we see the relationship between the enhanced and the current systems for these proxy variables. And so we see the pink systems, that's the current systems, they have a rather low correlation with the proxy variables, meaning that the instrument error is still quite significant. That is not reduced so much by longer observing times. Same thing over here. The current system for measuring CRF has an even lower correlation with its proxy variable, whereas the enhanced systems have much higher correlation. So the point of this whole demo is to illustrate how much bang for our buck we will get if we can launch this enhanced system. Okay, so let's get started, and I'm going to now fire up the program. This is the same graph as we just saw, however now the program is live. And so we have here the current systems in pink, the enhanced measurement systems in yellow. And now suppose in 2050 we can measure the rate percentage change in CRF, and we observe the value of 1. So that's a reasonably high value for this, it turns out. So how will this observation affect our knowledge of all of the other things in this graph? Well, that's simply a question of updating this distribution on that information. And we find that equilibrium climate sensitivity in expectation is now 3.87. It's gone up a fair amount. And the standard deviation has also gone up from 1.24 to 1.34. So, after this measurement, after having seen the value of 1, we are actually more uncertain about the predicted value for climate sensitivity than we were before. So imagine you have to go before Congress and explain, yes, thank you for all the billions of dollars to build this system, and the result is now that we know less about climate sensitivity than we knew before. Thank you very much. That's going to be a difficult story, but it can really happen, and this feature is called negative learning, and it's quite common, and it behooves us to educate both the scientists and the general public about this feature. So I'm going to now undo this measurement by unconditionalizing, and I want to conditionalize over here on the current system for measuring temperature, and I want to take a rather low value of 0.1. So if temperature goes up by 0.1 degrees centigrade per decade, it goes up by 1 degree in a century, and that's a fairly low value of equilibrium climate sensitivity. Let's update this. So you see that the expected value or predicted value is not 1, but is 2.25. quite a bit lower, but it's not 1 because of all the noise in these measurement systems. And now we could measure both systems. We have both teams up there and measuring, so let's put this other value in and see what happens. Okay, now we are measuring conflicting values. So the CRF measurement gave us a high value with expected value 3.87. The temperature gave us a low value, 0.1, with expected value 2.25. What happens when we put them together? Well, we get a prediction of 2.58 and a standard deviation of 0.67. So this value inclines more to the lower value from over here because this correlation is stronger than this one. But notice that the standard deviation has still gone down quite a bit. It was originally 1.24, now it's 0.678, almost 1/2. So there is a very strong lesson here. In spite of the fact that our measurements gave conflicting values, when we put them together, we can effect a sizable reduction in our uncertainty. Now, how is this possible? So I'm going to try to explain this just intuitively for you. Suppose we measure equilibrium climate sensitivity here, only this variable. Now, it's going to be deflected by the noise, and the noise could just as easily push this value up or down, right? We don't know which. But now we measure the second variable as well, and we have two values. Let me get this in the camera here. And now we can say that because of this higher value, that means that the noise in the lower value has probably deflected the value downwards. And the noise in the upper value has probably deflected it upwards. So in other words, if we have conflicting measurements, that means that our expected measurement errors have become negatively correlated. And that can give us a lot of information. So if we were to say, oh, the scientists don't agree, let's ignore them, that would be extremely stupid and mathematically just wrong, because the conflicting values does contain a lot of useful information, and if you use it, you can still effect a large reduction in uncertainty. So I'm now going to unconditionalize on these measurements, and I want to illustrate features about anomalies with concordant measurements by conditionalizing our enhanced system. So here I'm going to suppose that the CRF guys have measured the value 0.841. That's a fairly high value. And when we push this through the system, we will find that the expected value of climate sensitivity is 5.27, quite a bit higher. Well, that's nice to know. So let's now undo this one. And let's measure temperature, rate of temperature rise with the enhanced system, and suppose we get the value 0.4. Okay, our temperature team has come back with 0.4, and they run it through the software, and they find their prediction is also 5.27. Okay, hallelujah. The two teams have come back with exactly the same prediction, 5.27 from the decadal rate of temperature change, guys, and 5.27 from the cloud radiative forcing, guys. Great. So now these two teams get together and they say, well, we got the same value, so let's combine our measurements, and that will reduce our uncertainty from 0.841 to something lower. So we're going to do that. We're going to conditionalize now here on 0.841. We combine and we propagate both pieces of information through this network. And what do we find? Yes, the standard deviation went down to 0.738, but the mean value went up. So imagine these two guys coming together and they say, well, you got 5.27, same as me, so let's put our numbers together and predict 5.58. Right? So this again is very counterintuitive with respect to our naive ideas about how science and measurements work, and that's why we believe it's important that people can play around with these simple software tools and learn how they should think about measurements, both conflicting and agreeing. It's just not as simple as our naive intuitions would have us believe. Okay, that's the end of this simple video. Thanks for watching, and this is Roger Cook signing off for RFF.